Stride scheduling. While randomness gets us a simple and approximately correct scheduler, it occasionally will not deliver the exact right proportions, especially over short time scales. For this reason, Waldsperger invented stride scheduling, a deterministic share scheduler. Stride scheduling is also straightforward. Each job in the system has a stride, which is inverse in proportion to the number of tickets it has. So unlike randomly in lottery, stride strive to provide proportional share for each job with indirect proportion to the number of ticket it has. So remember in the previous video about scheduling, so we're going back to algorithms for scheduling. Another concepts or key when we're trying to discuss the fairness, because we discussed in the previous video that performance and fairness goes hand in hand when it comes to scheduling. In this case, we will use each job in the system as a stride, which we will and that is inverse in proportion to the number of ticket it has. In our example above, with jobs A, B, C with 150 and 250 tickets, which is this respectively, we can compute the stride of each by dividing some large number by the number of tickets each process has been assigned. So a large number divided by the number of tickets each job or process has been assigned. For example, if we divide 10,000 by each those ticket values, we obtain the following value for A, B, and C: 100, 240. So if we divide the 10,000 by 100, by the value we have earlier, we will get this 100, 240. So these are the stride value. We call this value stride of each process. Every time a process runs, we will increment a counter for it called its pass value by its stride to track its global progress. So every time each process runs, we will increment a counter for it called its pass value by its stride to track its global progress. So these are the representation of that. So you can see pass A start with 0, 0. As it start, we start with 100, right? And then next 100, 200, 0, 100, 240 until all of them matches. So the scheduler then uses the stride and pass to determine which process should run next. So the scheduler uses the stride to determine which job to process next. The basic idea is simple. At any given time, pick the process to run that has lowest pass value so far. When you run a process, increment its pass counter by stride. A pseudocode implementation is provided by Waldsperger here. Cur equal remove underscore min q, which means pick client with minimum pass, and then schedule current run for quantum, then cur pointing to pass plus equal cur pointing to stride, update pass using stride, and then insert parameter q comma cur, which return cur to the q, return current value to the q. In our example, we start with three processes A, B, and C with strides value of 100, 240, and all with pass values initially at 0. Thus, at first, any of the processes might run as their values are equally low. Assume we pick A arbitrarily. Any of the processes with equal low pass values can be chosen. A runs when finished with the time slice. We update its pass value to 100. Then we run B, whose value is then set to 200. Finally, we run C, whose pass value is incremented to 40. At this point, the algorithm will pick the lowest value, which is C, and run it. So at first, we start with A because that's the first in the queue. But later, we will pick the lowest value, which is C. As you can see here, we run this first and run it, updating its pass to 80. C stride is 40, as you recall. So we double it. We add 40 to it. Then C will run again, still lowest pass value, raising its pass to 120. A will run, now updating its pass to 200, now equals to B's. Then C will run twice more, updating its pass to 160, then 200. At this point, all pass values are equal again, and the process will repeat ad infinitum. So this is how it scheduled the processes. So in the previous video, we discussed multi-level feedback queue, in which you have an algorithm that tries to from time to time make all the process fair and performant, because it depends on our workload, right? We mentioned the block art on how we actually create this scheduler. There's no one solution. It really depends on your workload. But here, this scheduler is try to manage the processes using this stride, and that by the end of it, all the process has the same value. So that's one of the characteristics of stride. As we can see from figure C, C ran 5 times, A twice, and B just once, exactly in proportion to their ticket values of 250, 150. Lottery scheduling achieves the proportions probabilistically over time. Stride scheduling gets them exactly right at the end of each schedule cycle. So you might be wondering, given the precision of stride scheduling, why use lottery scheduling at all? Well, lottery scheduling has one nice property that stride scheduling does not: no global state. Imagine a new job enters in the middle of our stride scheduling example above. What should its pass value? Should it be set to 0? If so, it will monopolize the CPU. With lottery scheduling, there is no global state per process. We simply add a new process with whatever tickets it has, update a single global variable to track how many total tickets we have, and go from there. In this way, lottery makes it much easier to incorporate new processes in a sensible manner. So in this case, since these are all processes are interconnected, whenever we want to insert in the middle of the process, it will affect all this, because then if you have a 0, you will have to make it balance at the end. While lottery, you don't need we will discuss that in the future video, but basically for that scheduler algorithm, you don't have a global state. It doesn't relate. Let's say you enter a value in the middle of the process. So in this way, lottery makes it much easier to incorporate new processes in a sensible manner. As we will discuss, just like in data structures algorithm, it is very similar that in each every workload, it's also we also discussed this in design videos, that the structure and the algorithm we use depends really on our context. But basically, we're just discussing the most basic processes and how and what's the pros and cons of the scheduler available today in the modern operating systems. So let's discuss the Linux completely fair scheduler. So this is another part of proportional scheduling, which mean that these schedulers optimize for proportionality or fairness instead of performance. So for multi-level feedback queue, we optimize both, but here we're optimizing for fairness. But just because we're optimizing for fairness does not mean that we could insert, or that scheduler is not flexible from time to time to be optimized for performance. So this is where the Linux completely fair schedule comes in. So these scheduler are one of the most useful operating system, because again, there is a different operating system that is useful depending on your use for it. For example, for a virtual machine, this fair is perfectly sensible because you're optimizing for fairness in a virtual machine such as a cloud computing. But for a normal operating system, some task just requires more usage, CPU usage. So you need to optimize for those. For example, for consumer operating system. So completely fair scheduler. Despite these earlier works in fair sharing scheduling, the current Linux approach achieves similar goals in an alternate manner. The scheduler, entitled the Completely Fair Scheduler, implements fair share scheduler but does so in a highly efficient and scalable manner. So in the previous examples, it's not as scalable as this fair sharing or completely fair schedule by Linux. So to achieve its efficiency goals, CFS aims to spend very little time making scheduling decisions, though both its inherent design and its clever use of data structures well suited to the task. So it requires little time on thinking about the next scheduling decisions, unlike other algorithms we discussed, which achieve it through its inherent design and clever use of data structures well suited to the task. So again, it's about the right use of the right tool at the right time. So that's one of the hallmark of a good engineer. Recent studies have shown that scheduler efficiency is surprisingly important, specifically in a study of Google data centers, show that even after aggressive optimization, scheduling uses about 5% of overall data center CPU time, whereas most schedulers are based around the concept of a fixed time slice. CVS operates a bit differently. Its goal is simple: to fairly divide a CPU evenly among all competing processes. So you're trying to be fair, therefore you're gonna sacrifice this metrics or this configuration, which is the time slice. For most of the scheduler that we discuss, it has a fixed time slice or the interrupt. While here, it is dynamic depending on the process. So it does so through a simple counting based technique known as virtual runtime. So it introduced the counting techniques called virtual runtime. As each process runs, it accumulates vRuntime. In the most basic case, each process's vRuntimes increases at the same rate in proportion with physical real time. So it's kind of like tracking each process as it accumulates the runtime. Also, each process's vRuntime increases at the same rate in proportion with its physical runtime, or in how it actually directly uses the CPU. When a scheduling decision occurs, CFS will pick the processes with lowest vRuntime to run next. So the scheduler, or when the scheduling decision occurs, Instead of thinking what to decide, it already tracked that or count the VRAN time. So it will pick the process with the lowest VRAN time to run next. This raises a question. How does the scheduler know when to stop the currently running process and run the next one? The tension here is clear. If CFS switches too often, fairness is increased. As CFS will ensure that each process receives its share of CPU even over minuscule time windows. Obviously, if the CFS switches too often or context switch too often, you'll achieve more fairness but at the cost of performance, too much context switching. If CFS switch less often, performance is increased, reduce context switching but at the cost of near-term fairness. So this is the question, how does the scheduler know when to stop? So CFS manages this tension through various control parameters. So aside from that VRAN time tracking that process runtime, it also try to configure these various control parameters. So the first is sched latency. CFS uses this value to determine how long one process should run before considering a switch, effectively determining its time slice but in a dynamic fashion. So this is kind of like this sched latency is its new time slice, but it's dynamic or it changes for each process. A typical sched latency value is 48 milliseconds. CFS divides this value by the number of processes running on the CPU to determine the time slice for each for a process, and thus ensures that over this time period and thus ensures that over this period of time CFS will be completely fair. So it starts with this number 12 ms of virtual runtime, 48 ms of a sched latency, and this 48 ms is divided by the process running on that CPU. So we're just talking about one CPU here, so we're trying to be fair on all the process that's running on that particular CPU, so that over time, this period of time CFS will be completely fair. So it's the same with Stride. Over time, as it hits its maximum time or as it processes the request, it makes the share of these processes in the CPU fair. So for example, if there are n equal processes running, CFS divides the value of sched latency by n to arrive at a per process time slice of 12 ms. So 48 ms divided by 4 equals to 12 ms. CFS then schedules the first job and runs it until it has used 12 ms of virtual runtime, and then checks to see if there is a job with lower VRAN time to run instead. So since we divide each process at 12 ms and it tracks the runtime earlier, it now compare if there is a runtime that's less than that equal division, so that it will run that. So that's how it dynamically achieve the fairness of each processes having the same runtime, and checks to see if there's a job with lower VRAN time to run instead. In this case, there is, and CFS would switch to one of the three other jobs, and so forth. Figure 9.4 shows an example where for the jobs A, B, C, and D, each run for 2 time slices in this fashion. 2 of them, C and D, then complete, leaving just 2 remaining, which then each run for 24 ms round robin in 24 ms in round robin fashion. So here A, B, C, D, A, B, C, D, and then A, B, AB, AB. So this is our simple CFS example. But what if there are too many processes running? Wouldn't that lead to too small of a time slice and thus too many context switches? Good question. And the answer is yes. To address this issue, CFS adds another parameter, mean granularity, which is usually set to a value of like 6 ms. CFS will never set the time slice of a process to less than this value, ensuring that not too much time is spent in scheduling overhead. So it adds this another proper parameter, which is mean granularity, which says that the process could not be running less than 6 ms of time slice to make sure that not too much time is spent in scheduling overhead or in context switching. For example, if there are 10 processes running, our original calculation would divide sched latency by 10 to determine the time slice result 4.8 ms. However, because of mean granularity, CFS will set the time slice of each process to 6 ms instead, so that you don't have this too much context switching or too much scheduling. Although CFS won't quite be perfectly fair over the target scheduling latency, which is 48 ms, it will be close while still achieving high CPU efficiency. So this is what I'm saying. Just because it's able to provide those fair runtime to each processes does not mean it can't achieve this efficiency, as we can see by adding those simple parameters such as 6 ms, mean granularity, and dividing the the runtime, the processes by 48 ms, and then trying to run less than those runtime, and having those runtime to track each process are very valuable, or the keys, the parameter keys that allow us to do this algorithm. Note that CFS utilizes a periodic timer interrupt, which means it can only make decisions at fixed time intervals. These interrupts goes off frequently, every 1 milliseconds, giving CFS a chance to wake up and determine if the current job has reached the end of its run. So another thing is that CFS also has this periodic timer set to 1 milliseconds that gives this a chance to interrupt or wake up if the job has reached the end of its run. So aside from determining those parameters and letting it run over that period of time, it also has a power to stop the job after it finishes. If a job has a time slice that is not a perfect multiple of the timer interval, that is okay. If a job has a time slice that is not perfect multiple of the timer interval, that is okay. So if the time slice of that job is not perfect multiple of that timer interval set by this interrupt, it's okay. CFX tracks V runtime precisely, which means that over the long haul, it will eventually approximate ideal sharing of the CPU. So just because it's not the same at the interrupt time slice or multiple of time slice, does not mean we cannot create a scheduler that is fair, because in the previous video, like in a multi-feedback queue, we have this time slice multiple of our interrupts, but as we can see, we can actually create a track it via vruntime, mean granularity, and what you call that, sched latency. With those introductions, we were able to remove the need for a multiple of time interrupts for each processes, and therefore achieve a more fair processes for each CPU over time. Okay, it's almost the same as Stride, that it achieves those over time. CFS also enables control over processes priority. So it also has these parameters or control over processes priority, enabling users or administrators to give some processes a higher share of the CPU. It does this not with tickets, but through a classic Unix mechanism known as the nice level of a process. The nice parameter can be set anywhere -20 to +19 for a process with a default of 0. Positive nice value imply lower priority, and negative values imply higher priority. When you're too nice, you just don't get as much scheduling attention. Alas, so CFF maps the nice value of each process to a weight as shown here. So it maps that using a weight. So it has this, this is how it creates that using its data structure. -20 has a higher priority, so it's inverse. It's not, you may think that the positive is the first priority, but it's not. Additionally, aside from priority, it used that so aside from that completely sharing, in case you want to prioritize some process, you can. So it's kind of like more flexible, that allows you to balance or get the block art of the performance and fairness. Let's say you want this to be fair. It's also enable you to prioritize or to perform some processes. So here's the data structure for that. These weights allow us to compute the effective time slice of each processes, as we did before, but now accounting for their priority difference. So the formula to do so is as follows, assuming n processes. So these are the formula of weight that allow us to compute the effective time slice of each process. So how do you determine the time slice for each process? Let's say you add another a priority process. So let's do an example to see how this works. Assume there are two jobs, A and B. Because it's our most precious job, it's given a higher priority by assigning it a nice value of -5. B, because we hate it, just has the default priority nice value equals to 0. This means weight A from the table is 3121, where weight B is 1024. If you then compute the time slice of each job, you'll find that A's time slice is about 3 of sched latency, hence 3 ms, and B's about 1, hence 12 ms. So that's how we calculate the weight. As you can see, they have different time slice depending on their priority, or they have different weight depending on their priority. So as you can see in that, we have A time slice is about 3 of sched latency, hence 36 ms, and B is about 1, hence 12 ms. So remember, the sched latency is 48 ms divided by the number of process. But in this case, we determine the weight or the priority of different processes. And as we can see here, the time slice or the runtime of A is 36 ms because it has a higher priority, and B is about 12 ms because it has a lower time slice. So in addition to generalizing the time slice calculation, the way CFS calculates V runtime must also be adopted. Here's the new formula, which takes the actual runtime that process I has accrued runtime and scales it inversely by the weight of the process. So the runtime scales inversely by the weight of the process. By dividing the default weight of 1024 weight 0 by its weight. So in our example, A's V runtime will accumulate at 1/3 the rate of B's. So here, V runtime equals to V runtime plus weight 0 over weight 1 times runtime. So one smart aspect of the construction of the table ways above is that table preserves CPU proportionality ratios when the difference in nice value is constant. For example, if process A instead had a nice value of 5, not -5, and process B had a nice value of 10, not 0, CFS would schedule them in exactly the same manner as before. Run through the math yourself to see why. So because of that, we only have A and B. The -5 and the 0 and 5 and 10 has the same schedule because those are being adjusted in proportion of the processes available on the system. So since they are both the same spatial or the same five step below and above each other, therefore they have the same scheduling time by the scheduler. So again, the weight allow us to determine the runtime or the time slice that we will provide to the process and how long it will be able to use our CPU, because again, this is how we prioritize the process. One smart aspect of the construction of the table of weights above is the table preserves CPU proportionality ratios when the difference in nice value is constant. For example, process A instead had a nice value of 5, not -5, and process B had a nice value of 10, not 0. CFS would exactly schedule them. So one of the things that is advantage of this is that it calculates the priority dynamically depending on the processes available on the system. So it's kind of like allows you to dynamically change it automatically without even thinking about it. So one major focus of CFS is efficiency, as stated above. For a scheduler, there are many facets of efficiency, but one of them is as simple as this. When the scheduler has to find next job to run, it should do so as quickly as possible. Simple data structures list don't scale. Modern systems sometimes are comprised of thousands of processes, and thus searching through a long list every so milliseconds is wasteful. So a list data structure, as discussed in the previous video, will take this an ON time. So we don't need that in CFS. So we have to use a different data structure. CFS addresses this by keeping process in a red block tree. So a red block tree is one of many types of balanced trees. In contrast to a simple binary tree which degenerate to list like performance under worst case insertion patterns. For binary tree, the insertion in worst case scenario is the same as least, but in balanced trees, it's O log n. So balanced trees do a little extra work to maintain low depths and thus ensure that operations are logarithmic and not linear in time. CFS does not keep all processes in this structure. Rather, only running or runnable process are kept therein. So not all the processes are in this structure when tracking it by the CFS. Only the running or runnable processes. If a process goes to sleep, say waiting on an IO to complete or for a network packet to arrive, it is removed from the tree and kept track of elsewhere. Let's look at an example to make this more clear. Assume there are 10 jobs and that they have following values of VRAN time: -1, 5, 9, 10, 14, 18, 17, 21, 22, and 24. If we kept these jobs in an ordered list, finding the next job to run would be simple. Just remove the first element. However, when placing the job back into the list in order, we would have to scan the list, which is ON, looking for the right spot to insert it. Any search is also quite inefficient, also taking linear time on average. Keeping the same values in a red block tree makes most operation more efficient. So the insertion, deletion, searching, and reading are more efficient in red block tree. Processes are ordered in tree by VRAN time. So these are ordered by its VRAN time, which we tracked earlier. And most operations such as insertion and deletion are logarithmic in time, which is O log n. So I think there is a similarity of with heap, or I forgot the trees, but we discussed that it's a kind of tree where the insertion and deletion are logarithmic as well. Yeah, I think that's heap. When n is the thousands, logarithmic is noticeably more efficient than linear. Why? Because that 1000 will be in a division of 2, which means that to get to 1000, we just need 2 raised to 10, I think, 10 times or 10 steps to get to 1000 instead of 1000 steps using the linear search. So dealing with IO and sleeping processes, one problem with picking the lowest VRAN time to run next arises with jobs that have gone to sleep for a long period of time. Imagine 2 processes A and B, one of each A runs continuously and the other B, which has gone to sleep for a long period of time, say 10 seconds. When B wakes up, its VRAN time will be 10 seconds behind A's, and thus, if we're not careful, B will now monopolize the CPU for the next 10 seconds while it catches up, effectively starving A. So we don't want that because we want a fair share, especially in CFS. So CFS handles this by this case by altering VRAN time of a job when it wakes up. Specifically, CFS sets the VRAN time of that job to the minimum value found in the tree. So since it tracks the runtime in the tree, it sets that recently woke up job with the lowest value. In this case, it's 1. Remember, the tree only contains running jobs. So in this way, CFS avoids starvation, but not without a cause. Job that sleeps for a short period of time frequently do not ever get their fair share of the CPU. So this is its weakness. So for jobs that sleep frequently, it doesn't get the fair share of the CPU because again, you always get this lowest value of the red block tree. Other CFS fun. So CFS has many other features. It includes numerous heuristics to improve cache performance, has strategies for handling multiple CPUs effectively, can schedule across large group of processes instead of treating each process as an independent entity, and many other interesting features. Again, CFS has many other features. It includes numerous heuristics to improve cache performance, has strategies for handling multiple CPUs effectively, can schedule across large group of processes instead of treating each process as an independent entity, and many other interesting features. So it also has cache performance that allows you to um, increase the performance. Since it's optimized for fair share, you can introduce a cache for increased performance for the process you want. It also has strategies for handling multiple CPUs like multiprocessor, and schedule large group of processes instead of treating each processes at once. So you can even group processes and then determine their priority on the system, and many other interesting features. So tip: use efficient data structures when appropriate. In many cases, a list will do. In many cases, it will not. Knowing which data structure to use when is a hallmark of good engineering. In the case discussed herein, simple lists found in earlier schedules simply do not work well on modern systems, particularly in the heavy loaded servers found in data centers. Such systems contain thousands of active processes. Searching through a long list to find the next job to run on each core every few milliseconds would waste precious CPU cycles. So the list does not work in heavily loaded servers found in modern data centers today, because it has thousands of active processes. So searching through a list to find it would be end time. Every few milliseconds would waste precious CPU cycles. So a better structure was needed, and CFS provided one by adding an excellent implementation of a red block tree. More generally, when picking a data structure for a system you are building, carefully consider its access pattern and its frequency of usage. By understanding this, you will be able to implement the right structure for the task at hand. So again, it's kind of like in the design videos, the interactive or the product depends on how it is being used. So as you can see here, the data structure or DCFS are used in modern data system because of its frequency of usage and access patterns. So it's kind of like in workloads as well, like we discussed in multi-level feedback queue. It depends on your workload in and the process. So the more you know about the workload, the specific task you are dealing with, the better you are to determine what data structure to use in your system. So lottery uses randomness in a clever way to achieve proportional share. Stride does so deterministically. CFS, the only real scheduler discussed in this chapter. So the lottery and Stride is just a concept of data structures that could provide a proportional share on the CPU, but it's not implemented in a modern scheduler. So the only real scheduler that we discuss is a CFS. It's a bit like a weighted round robin with dynamic time slices. Again, weighted round robin. So it allows you to determine the priority. That's why it's weighted round robin with the dynamic time slices, but built to scale and perform well under load. So to our knowledge, it is the most widely used fair share scheduler in existence today. No scheduler is panacea, and fair share schedulers have their fair share of problems. One issue is that such approaches do not particularly mesh well with I/O, as mentioned above, because for I/O you're not gonna get the fair share because you're always taping and may not get their fair share of CPU. Another issue is that they leave open the hard problem of ticket or priority assignment. So another problem with this is that the priority assignment. So how do you prioritize since the system are designed to get a fair share? Because inherently when you're trying to prioritize, you're trying to optimize the system for performance as well. So how do you know how many tickets your browser should be allocated, or to what nice value to set to your text editor. Other general purpose schedulers such as the MLFQ we discussed previously and other similar Linux schedulers handle these issues automatically and thus may be more easily deployed. So the MLFQ handles the priority efficiently, but it may not get the fair share. So you can see there's this pros and cons with performance and fairness. So the good news is that there are many domains in which these problems are not dominant concerns and proportional share scheduler are used to great effect. For example, in a virtualized data center or cloud where you might like to assign 1/4 of your CPU cycles to the Windows VM and the rest to your base Linux installation. Proportional sharing can be simple and effective. The idea can also be extended to other resources. So see Walsperger for further details on how to proportionally share memory in VMware's ESX server. Multiprocessor scheduling advanced. So in the previous schedulers we discussed how will scheduler work in one CPU. Here we will discuss a multi-processor scheduler. So we discuss specifically the CFS for fair scheduling and multi-level feedback queue which balance performance and fairness. Here we will discuss what are the schedulers that are actually used for multiprocessor world of the modern system. So after years of existence, only in the high end of computing spectrum, multiprocessor systems are increasingly commonplace and have found their way into desktop machines, laptops, and even mobile devices. The rise of the multi-core processor in which multiple CPU cores are packed onto a single chip is the source of this proliferation. These chips have become popular as computer architects have had a difficult time making a single CPU much faster without using way too much power. So the rise of the multi-core processor in which multiple CPU cores are packed onto a single chip is the source of this proliferation. So in a single chip, you have a multiple CPU today. Now these chips become popular as computer architects have had a difficult time making a single CPU much faster without using way too much faster. So the reason why we have a multiprocessor or multiple CPU in a single chip is because computer architects have a hard time to make the CPU handle more processes without increasing or consuming too much power. So of course, there are many difficulties that arise with the arrival of more than a single CPU. A primary one is that a typical application, some C program you wrote, only uses a single CPU. Adding more CPU does not make that single application run faster. To remedy this problem, you'll have to rewrite your application to run in parallel. Perhaps using threads, multi-threaded applications can spread work across multiple CPUs and thus faster when given more CPU resources. So you now know there's a limitations on this one CPU, though people may want faster, or it may be easier to create all the programs in one CPU, but it seems like that's a limitation of our physics or engineering today, that we require multiple processor. That's why we adjusted. So we write our programs using a multi-threaded way or in parallel so that we can take advantage of this multiprocessors. So instead of the engineering adjusting to our needs, we actually adjust the software to accommodate this multi-threaded or multi-threaded or multi-processor chip. So beyond application, a new problem that arises for operating system is not surprisingly that of multiprocessor scheduling. So beyond that application or creating a multi-threaded or parallel application, a new problem arises also for operating system, which is a multiprocessor scheduling. So it's not only a problem of the programmer writing in C, it's also problem of the OS programmer that write the operating system. Thus far, we discussed a number of principles behind single processor scheduling. How can we extend those ideas on to work on multiple CPUs? Of course, we cannot go far from the principles we already established on the CPU. So the better question would be, how do we use those principles to use on our multiprocessor CPU? So crooks, how to schedule jobs on multiple CPUs. How should the OS schedule jobs on multiple CPUs? What new problem arise? Do the same old techniques work, or are there new ideas required? So here's a diagram of how it looks like: CPU, cache, memory. So these are the hint. We will use cache to be able to serve the process more efficiently. Background, multiprocessor architecture. To understand to understand the new issues surrounding multiprocessor scheduling, we have to understand new and fundamental difference between single CPU hardware and multi-CPU hardware. So to understand how to optimize it, we need to first understand the difference between single and multiple CPU hardware. The difference centers around the use of hardware cache, like in this figure 10.1. And exactly how data is shared across multiple processes. We now discuss this issue further at a high level. In a system with a single CPU, there are hierarchy of hardware caches that in general help the processor run programs faster. Caches are small, fast memories that in general hold copies of popular data that is found in the main memory of the system. So for a single CPU, there are actually a hierarchy of hardware. So the first is that small fast memory, which is cache, and a more slow general memory. So here's an example, that figure 10.1, to help the processor run program faster. Now caches are small fast memories that in general copies are popular data that is found in main memory of the system. So that cache is a popular data that is found in main memory of the system. So it actually get it from how the user use or the programmer use the system or the memory. So it gets that data, it put that in this small cache. In contrast, main memory in contrast holds all of the data, but access to this larger memory is lower. By keeping frequently accessed data in a cache, the system can make the large slow memory appear to be a fast one. So by keeping those is what actually makes our system faster. So our memory is inherently slow, but because of that slow cache for most popular items, because again in the about face chapter we discuss how only a few simple things we do use usually, because 95% of our habit are automatic. So the system or the memory just optimize the data or the cache of this based on those frequently used behaviors. That's what make the memory access of memory fast. So as an example, consider a program that issues an explicit load instruction to fetch a value from memory, and a simple system with only a single CPU. The CPU has a small cache, say 64 kilobyte, and a large main memory. So let's say this is a 64 kilobyte, and the program issue or fetch a load instruction to fetch a value from memory. The first time a program issues this load, the data resides in memory and thus takes a long time to fetch, perhaps in the tens of nanoseconds or even hundreds. The processor, anticipating that the data may be reused, puts a copy of the loaded data into the CPU cache. So the CPU notice that or anticipate that it will be reused, so puts a copy of the loaded in the CPU cache. So it's also being done in the virtualization of memory, as we will discuss in the future videos. So it does that using the temporal locality, which means that if you access it once, you'll likely have to access it again, since that process have been accessed by the program. Sorry, that data has been accessed by the program. Therefore, it is likely be accessed again. So the CPU will try to save that. So if the program later fetches this same data again, the CPU first checks for it in the cache. It finds it there. The data is fetched much more quickly, say just a few nanoseconds, and thus the program runs faster. So that's how we done it in the single CPU. So you can see we can already do that in a single CPU. So how do we do that in multiple processors? So that's the question. Caches are thus based on the notion of locality, of which there are two kinds: temporal locality and spatial locality. The idea behind temporal locality is that when a piece of data is accessed, it is likely to be accessed again in the near future. Imagine variables or even instructions themselves being accessed over and over again in a loop. So that instruction, like the function and the variables it has, being accessed by a loop, because that most program consists of. So the idea behind spatial locality is that if a program accesses a data item at address X, it is likely to access data items near X as well. So this is where the virtualization of memory as well, because if you access that in that virtual address X, which map to the physical address, let's say A, therefore if you access the virtual address Y, you're likely to access it in a physical address B because of its spatial locality. Here, think of a program streaming through an array or instructions being executed one after the other. Because locality of this type exists in many programs, hardware system can make good guesses about which data to put in cache and thus work well. So it's like in a design as well. The hardware could also make guesses, since you're accessing it most of the time. You can distinguish the probability with possibility. So it's probable that it will happen, and it will be because we're a creature of habit. Therefore, you can cache it because you have access it, and then you know that this type of memory are accessed by this type of memory. Therefore, you would access it in the same location at this memory. So this is how cache are created. Now, for the tricky part, what happens when you have multiple processors in a single system with a single shared memory, as we will see in figure 10.2. So what happens if this is the case? Imagine, for example, that a program running on CPU 1 reads a data item with a value D at address A. Because the data is not in the cache on CPU 1, the system fetches it from main memory and gets this value D. The program then modifies the value at address A, just updating its cache with newer value D. Writing the data through all the way to main memory is slow, so the system will usually do that later. So since it never had accessed it before, and it will access the main memory. For that, it will the CPU will do that later because it will take time. Then assume the OS decide to stop running the program and move it to CPU 2. So the program then rereads the value at address A. There's no such data in CPU 2's cache, and thus the system fetches the value from main memory and gets the old value D instead of the correct value, which has been modified. But since it took time, it has this like synchronization issue. Oops. This is general problem is called the problem of cache coherence. It's actually cache coherence. We're not yet on synchronization, but it has the same idea. But this cache coherence just works in a low level mechanism, and there's a vast research literature that describes many different subtleties involved with solving the problem. So that's the problem with multiprocessor, because you can move to different CPU, therefore it can modify the same data that you have waited in the first process. So the basic solution is provided by the hardware. By monitoring memory access, hardware can ensure that basically the right thing happens, that the view of a single shared memory is preserved. Again, the basic solution is provided by the hardware. By monitoring memory access, hardware can ensure basically the right thing happens and that the view of a single shared memory is preserved. So how do you solve that? By tracking again, kind of like in vRuntime with CFS. So it allows you to have a dynamic time slice because you track the you track the runtime of each processes for that one CPU. Here we're gonna track we're gonna use the hardware to track the memory access of each CPU to make sure we don't do duplicate actions. So one way to do this is on a bus-based system, as described above, is to use an old technique known as bus snooping. So these are a technique that we were gonna use for multiprocessors. So each cache pays attention to memory updates by observing the bus that connects them to main memory. So this cache, the hardware allow us to do this by using this cache, by having this cache tracking or paying attention to memory updates by observing the bus that connects them to main memory. So it uses a bus to notify them of the updates on the main memory. So when a CPU then sees an update for a data item it holds in its cache, it will make the change and either invalidate its copy, remove it from its own cache, or update it. So it will either remove it, delete it, or edit it and put the new value into its cache too. Write-back caches, as hinted at above, make this more complicated because the write to main memory isn't visible until later. So a write-back caches is more complicated to implement because the write to main memory isn't visible until later after the slow memory has processed it. But you can imagine how the basic scheme might work. So here, don't forget synchronization. Given that caches do all this work to provide coherence, do programs or the OS itself have to worry about anything when they access shared data? The answer, unfortunately, is yes. So aside from hardware, the program and OS needs to know or worry about when they are accessing data, and this is how we achieve this in multiprocessor. When accessing and in particular updating shared data items or structure across CPU, mutual exclusion primitives such as locks should likely be used to guarantee correctness. Other approaches such as building lock-free data structures are complex and only used on occasion. See the chapter on deadlock in the piece of concurrency for details. So we only build, use a lock-free data structure occasionally because it's complex. But for this, share data items or structure across CPU mutual exclusive primitives such as locks should likely be used to guarantee correctness. So we will use a mutual exclusion for this program and OS to guarantee correctness aside from hardware to guarantee or to solve this synchronization issue. For example, we have a shared queue. So this is also the issues with a lot of programming or web applications today, where you have this overwriting memories and CPUs under the hood that makes it unsynchronized. So this synchronization is a big problem in modern systems, especially when you're writing this multi-threaded application. So for example, we have a shared queue being accessed on multiple CPUs concurrently. So for example, we have created a shared queue being accessed on multiple CPUs concurrently by our multiple cache that updates by the bus. So without locks, adding or removing elements from the queue concurrently will not work as expected, even with the underlying coherence protocols that allow us to avoid that cache coherence using the cache in each CPU. One needs locks to atomically update the data structure to its new state. So again, this is how lock works. This is also the most useful process, or a process that is optimized by the stub allocator. So to make this more concrete, imagine this code sequence which is used to remove an element from a shared linked list. As we see in figure 10.3, imagine if threads on two CPUs enter this routine at the same time. So if thread 1 executes the first line, it will have the current value of head stored in its TMP variable. If thread 2 then executes the first line as well, it will also have the same value of head stored in its own private TMP variable. TMP is allocated on the stock, and thus each thread will have its own private storage for it. So these are the classic example where two threads or two CPU try to execute same line of code. So thus, instead of each thread removing an element from the head of the list, each thread will try to remove the same head element, leading to all sorts of problems such as attempted double free of the head element at line 10, as well as potentially returning the same data value twice. So you have this double free, which is an issue with freeing memory, right? You also have this potential of returning the same data value twice. So you get the same data values twice to your process. So again, it is a shared linked list. So remember the linked list, it's a data structure, a node data structure. So for this, it's a classic problem of synchronization for, it's a program that, type of program that has this structure will have this problem for this multi-threaded or multiple CPU cache. Now, the solution of course is to make such routines correct via locking. So the solution for this is via locking for the program, the process, and then OS coordination. not just the CPU, because we already implemented the CPU cache. In this case, allocating a simple mutex like pthread mutex tm. So we discussed this pthread when creating the thread before, but this is some more details on why we actually do that pthread. So these are pthread are actually implement those locking that allows the structure to be implemented in multiprocessors, and then adding a lock nm at the beginning of the routing and an unlock nm at the end will solve the problem, ensuring that the code will execute as desired. So remember the nm after the pre-thread and before the pthread code in the previous video. Unfortunately, as we will see, such an approach is not without problems, in particular with regards to performance. So since we make this, a concurrent processor using a program by writing it with nm and pthread, there is a performance issue that we need to accept. So if we want the synchronization and the advantage of this CPU, multiple CPU, we need to sacrifice performance. Specifically, as the number of CPU grows, access to asynchronous shared data structures become quite slow. So how do we fix the scalability issue as the CPU grows to make it synchronized, as well as to utilize this multi-processors with our program data structure? So one final issue, cache affinity. One final issue arises in building a multi-processor cache scheduler known as cache affinity. So in building a multi-processor cache scheduler, so a scheduler that optimizes with this cache with the multi-processor is a cache affinity. So this notion is simple. A process, when run on a particular CPU, builds up a fair bit of state in the caches and TLBs of the CPU. So this TLBs, we will discuss that in the previous video. It's a type of caches but in virtual memory. The next time the process run, it is often advantageous to run it on the same CPU, and it will run faster if some of its state already present in the caches on the CPU. So once you run the program on that CPU, you don't want that to run that on a second CPU, because you will have to copy that. So instead, you want to continue or maximize that first already initialized state. So this is what the cache affinity is all about. So if instead one runs a process on a different CPU each time, the performance of the process will be worse, as it will have to reload the state each time it runs. So it will reload the state each time it runs, or the program counter. Note it will run correctly on a different CPU thanks to the cache coherence protocol of the hardware. So because the cache now listens or notifies by the bus and with the main memory, it will run correctly, but with the performance issues. Thus, a multiprocessor schedule should consider cache affinity when making its scheduling decision. So perhaps preferring to keep a process on the same CPU if it at all possible. So since there is this cache affinity and synchronization problem, you want to write a code in your program and then operating system to be able to run that program in one CPU as much as possible, because once it has that state, it is easier to run on that or to keep the momentum. So single scheduling. With this background in place, we now discuss how to build a scheduler for multiprocessor system. The most basic approach is to simply reuse the basic framework for single processor scheduling by putting all jobs that need to be scheduled into a single queue. We call this single queue multiprocessor scheduling, or SQMS for short. So first, we can actually reuse the single processor scheduling in multiprocessor by putting all jobs need to be scheduled into one or a single queue. So that's actually SQMS for sure. This approach has the advantage of its simplicity. It does not require much work to take an existing policy that picks the best job to run next and adopt it to work on more than one CPU, where it might pick the best two jobs to run if there are two CPUs, for example. However, SQMS have obvious shortcomings. The first problem is a lack of scalability. To ensure the scheduler works correctly on multiple CPUs, the developers will have inserted some form of locking into the code. As described above, locks ensure that when SQMS code accesses the single queue, say to find the next job to run, the proper outcome arises. Locks unfortunately can greatly reduce performance, particularly as the number of CPUs in the systems grow. So you can definitely do this, but with a more complex code, because you need to consider lock when creating these data structures and algorithms or program. And also these locks that you created reduce performance, particularly as the number of CPUs in the system grows. As contention for such a single lock increases, the system spends more and more time lock overhead and less time doing the work the system should be doing. The second problem with SQMS is cache affinity. So cache affinity, we have discussed that, with multiprocessor. For example, let us assume we have 5 jobs to run, A, B, C, D, E, and 4 processors. Our scheduling queue does look like this. So we have 5 jobs and 4 processors. So over time, assuming each job runs for a time slice and then another job is chosen, here is a possible job schedule across CPUs. So as you can see, it's scattered. Because each CPU simply picks the next job to run from the globally shared queue, each job ends up bouncing around from CPU to CPU, thus doing exactly the opposite of what would make sense from standpoint of cache affinity. So single or the recycled scheduler from a single processor, which is just choosing the best job to run at the moment, which is the multi-level feedback queue, does not work well here because of the problem of cache affinity and cache affinity and synchronization of multiprocessor. As you can see, it's not spread or the scramble on multiple CPU instead of optimizing the running process in one CPU. So to handle this problem, most SQMS schedulers include some kind of affinity mechanism to try to make it more likely that process will continue to run on the same CPU if possible. Specifically, one might provide affinity for some jobs but move others around to balance load, thus achieving some kind of affinity fairness as well. So we want to achieve an affinity fairness when it comes to the CPU. It's not the time slice, but with regards to a CPU. Implementing such a scheme, however, can be complex. For example, imagine the 5 jobs scheduled as follows. So here we can provide an affinity mechanism for this SQMS, recycle the previous multi-level feed queue and implement this mechanism that allow us to sacrifice some processes that allows still to get the same CPU affinity to accomplish this same state or same CPU for each processes. However, it's complex and it might not worth your time creating that algorithm. Thus, we can see the SQMS approach has its strengths and weakness. It is straightforward to implement given an existing single CPU scheduler, which by definition has only a single queue. However, it does not scale well due to synchronization overhead, and it does not readily preserve cache affinity. So again, that's the problem with multiprocessor, which is the synchronization and cache affinity. So the previous scheduler we have created, which is the multi-feedback level queue, does not scale well. Multi-queue scheduling. So because of the problem caused in a single queue scheduler, some systems opts for multiple queues, one per CPU. So we have created a multiple queues for each CPU. So we call this approach multi-queue multiprocessing scheduler, or MQMS. In MQMS, our basic scheduling framework consists of multiple scheduling queues. Each queue will likely follow a particular scheduling discipline, such as a round robin, though of course any algorithm can be used. So since we have this separate, this is how we manage that synchronization and cache affinity. We could have a different algorithm depending on our choices or what most effective for that workload. When a job enters the system, it is placed on exactly one scheduling queue, according to some heuristics like random or picking one with fewer jobs than others. So when jobs enter the system, it enters a queue or one scheduling queue according to some like parameters, either the one with fewer jobs than the others, like queue that has fewer jobs than the others, or randomly. Then it is scheduled essentially independently, thus avoiding the problems of information sharing and synchronization found in the single queue approach. For example, assume we have system where there are just two CPUs labeled CPU 0 and CPU 1, and some number of jobs enter the system, A, B, C, and D for example. Given that each CPU has a scheduling queue now, the OS has to decide into which queue to place each job. It might do something like this, like Q0 you have A, Z job, Q1 B, D job. So depending on the queue scheduling policy, each now has two jobs to choose from when deciding what should run. For example, with round robin, the system might produce a schedule that looks like this. Another thing is that, let's say you can also implement in this scheduler something like determine the process, like if it's a short running process or long running process, and create a queue for short running process and long running process, and then try to create some parameter or control, just like the CFS, kind of like a runtime or schedule latency that allows you to decide which processes to run next to achieve this fairness and performance in the system. So as you can see here, CPU 0, AACC they both use a round robin, and they act on the process twice, or they have a time slice of 2 for each process. So MQMS has a distinct advantage of SQMS in that it should be inherently more scalable. As the number of CPU grows, so too does the number of queues, and thus lock and cache contention should not become a central problem. So this solved now the problem of scaling and the cache affinity and synchronization, because as the number of CPU grows, so does the queues, because each CPU has its own queues. In addition, MQMS intrinsically provides cache affinity. So because of that, we don't need as much to worry about those BAS or the cache that notifies this large memory or the slow memory, or updates with that large memory, because each queue or this implementation inherently implements that. So jobs stay on the CPU and thus reap the advantage of reusing cache contents therein. So because that job stay on that one CPU until the end of its process, it reaps the advantage of reusing cache contents therein. Therefore, it processes it more quickly. But if you've been paying attention, you might see we have a new problem, which is fundamental in the multi-queue based approach: load imbalance. So let's assume we have the same setup as above, 4 jobs, 2 CPUs, but then one of the jobs, say C, finishes. We now have the following scheduling queues: Q0 A, Q1 B, D. If we then run our round robin on each queue of the system, we will see this resulting schedule. So as you can see, we don't achieve the fairness. So As we can see from this diagram, A gets twice as much CPU as B and D, which is not the desired outcome. Even worse, let's imagine that both A and C finish, leaving just B and D in the system. So the two scheduling queues and resulting timeline will look like this. So it doesn't achieve this fairness in a load imbalance system. So this is its weaknesses or its weakness. So how terrible. CPU 0 is idle. So insert dramatic and sinister music here. So how do we how to deal with load imbalance? How should a multi-queue processor scheduler handler load imbalance achieve its desired scheduling goals? So the obvious answer to this query is to move jobs around, a technique which we once again referred to as migration. So we already discussed it is in single queue scheduler, but it's complex to implement. But here it's easier to implement. It's like migration. By migrating a job from one CPU to another, true load balance can be achieved. So this is how we will use that migration we use in XQMS. So let's look at a couple of examples to add some clarity. Once again, we have situation where one CPU is idle and the other has some jobs. So in this case, the desired migration is easy to understand. The OS should simply move one of B or D to CPU 0. Now the result of this single job migration is evenly balanced and everyone is happy. A more tricky problem arises in our earlier example where A was left alone on CPU 0 and B and D were alternating on CPU 1. So this is another more complicated or sophisticated problem. In this case, a single migration does not solve. So when 1-0 or load imbalance, like you have two processes on Q1 and no process on Q0, it's easier to balance, right? But a more tricky arises when you have one and then two on the one on Q0 and two on Q1. So in this case, a single migration does not solve the problem. What do you do in this case? The answer, alas, is continuous migration of one or more jobs. One possible solution is to keep switching jobs, as we see in the following timeline. So a continuous migration, so instead of like migrating the other, like noticing if you're probably gonna use a code like if this Q0 is equals to 0 or no jobs, and this has more than one jobs, you're gonna switch it here. But the code that you're gonna use there is a round robin. So if Q0 has 1 and Q1 has BD, you're gonna do a round robin by migrating or alternating on both queues. So one possible solution is to keep switching job, as you see in the following timeline. In the figure, first A is alone on CPU 0 and B and D alternate on CPU 1. After a few time slices, B is moved to compete with A on CPU 0. So we do that after some time slices. So if, like, we're gonna use some if statement there on the code, while D enjoys a few time slices alone on CPU 1, and thus load is balanced, as you can see in this representation. Of course, many other possible migration patterns exist. So not just round robin, other techniques or patterns also exist. But now for the tricky part, how should the system decide to enact such migration? One basic approach is to use a technique known as work stealing. So it's not actually a round robin, it's a work stealing algorithm. So they use a work stealing. With the work stealing approach, a source queue that is low on jobs will occasionally peek at another target queue. So if that queue that lows on job will if that queue is low on job, it will peak. So it is the action of this queue that have less SIR jobs will pick on another queue to see how full it is, rather than this checking if this have 0. So that's the algorithm. If the target queue is notably more than full than the source queue, the source will steal one or more jobs from the target to help balance load. Of course, there is a natural tension in such an approach. If you look around at other queues too often, you will suffer from high overhead and have trouble scaling. So if you look often using this approach or work stealing, you will suffer trouble scaling because you're gonna have high overhead or scheduling overhead looking for other queues, which was the entire purpose of implementing multiple queue scheduling in the first place. If on the other hand you don't look at other queues very often, you are in danger of suffering from severe load imbalance. Finding the right threshold remains, as is common in system policy design, a black art. Linux multiprocessor schedulers. Interestingly, in the Linux community, no common solution has emerged to building a multiprocessor scheduler. Over time, 3 different schedulers arose. Both O1 and CFS use multiple queues. So the CFS we discussed earlier that tries to achieve proportional share use multiple queues, whereas BFS use a single queue. So BFS uses the SQMS, which is a bit a unique way of applying it, which shows that both approach can be successful. Of course, there are many other details which separate these schedulers. For example, the O1 scheduler is a priority-based scheduler, similar to the MLFQ discussed before. So the MLFQ for single processor is that we discussed previously is actually a priority-based. So it optimizes per performance rather than fair share or proportional share. It's changing a process priority over time and then scheduling those with highest priority in order to meet various scheduling objectives. Interactivity is a particular focus, just like in MLFQ, right? We maximize the interactivity there and the response time. We maximize interactivity using the response time and turnaround time. CFS, in contrast, is a deterministic proportional share approach, so it strives to make the process have a fair share on the system as discussed earlier. BFS, the only single queue approach among the three, is also a proportional share, but based on a more complicated scheme known as earliest eligible virtual deadline first. So we have seen a various approach for multiprocessor scheduling. The single queue approach, SQMS, is rather straightforward to build and balances load well, but inherently has difficulty with scaling to many processors and cache affinity. So SQMS is a straightforward but has a difficulty of scaling in multiprocessors because of synchronization and cache affinity. The multiple queues approach, MQMS, scales better and handles cache affinity well because the structure are just inherently designed to maximize the cache content of the previous process executed to it, but has trouble with load imbalance. So it has a weakness with load imbalance or the fairness on how the CPU execute loads because it must constantly work still, which is the purpose of multiple queue approach at the first place. And is more complicated. So whichever approach you take, there is no simple answer. Building a general purpose scheduler remains a daunting task as small code changes can lead to large behavioral differences.